In part 2 here, let's go through how we're going to check each assumption in R and see all the different ways we can do that. And everything again is detailed here, so you should have no problem reading through it and let me know if something doesn't make sense. And what I've done is I've shown you how to do something each time 3 different ways. So that's why this looks longer than usual. So, all right, we've collected predicted values and residuals and also standardized residuals. Now we're going to use the residuals and also the predicted values to check the assumptions of our model. Because remember, just because we run a model and get some numbers for it, doesn't mean that it's reliable. It doesn't mean that we can use it to make the conclusions that we want to make. So to actually check the assumptions that need to be satisfied, R and some graphs will help us with that. So the first assumption is linearity. Remember, we want there to be a linear relationship between the response variable and the explanatory variable. Best way to do that is to run your initial scatter plot. So you will have already seen this. And remember, we're modeling the number of games won as explained by points per game. So all I need to do is look at the initial scatter plot of my data, points per game on the x-axis, games won on the y-axis, and say, does that look like there is some kind of linear relationship going on there? Yeah. In other words, I don't see curvature. I don't see some kind of exponential thing or some kind of parabola kind of shape. I can't think of any other thing other than a line to help fit this. So yeah, linearity looks good. So moving on to the second assumption. Now I put this in here, this explanation, but as you might have been able to guess, we generally don't check independence with graphs. There's a very specific case in dealing with time series data that's more common in economics. That it's a very special case. When we check the assumption of independence in this class, all we do is we ask the question, does one y value influence another y value? Sorry for the gap there. I wanted to get my wording right. So if we generally don't think about violations of independence unless there's a really clear situation where one value of our response variable somehow influences another value of our response variable. So there's nothing in R to check. It's just a logical deduction. And check the lecture again for a little bit more about independence, because I definitely talk a lot more about it there. Now on to the third assumption, which is straightforward. It's the normality of the residuals. We need these residuals to be normally distributed in order to make the conclusions that we want to make. And we'll see that a little bit next week. So there are 3 different types of plots you can use to do this. And I recommend, at least for now, that you run all 3 when you are checking normality, because that will give you the best possible information for judging whether or not your residuals are normally distributed. So the first plot you can run is a histogram. And you've seen a histogram before. And there are 3 different ways you can run this histogram. This may seem tedious, but I just want to give you all the options possible to do whatever works best for you. If you remember up above, I stored the name of my residuals as lm.1resid. So I can just say histogram lm.1 resid. And there's a histogram of my residuals. If you remember, in order for me to get that lm.1 resid, that thing that I made, I used the function resid and then the name lm.1. You can then, if you want, instead of running and saving it as something, you can just nest that command within the histogram function as I have here. And it'll give you the exact same thing. Slightly different title. Alternatively, as we did at the end here, if you put everything in a data frame, you can just call those residuals from the data frame you made. And again, it just changes the titles of things. But those are 3 ways to get a residual, a histogram of the residuals. And you can do the exact same things with the standardized residuals. You can use all these 3 methods I have above. But let's just look at this momentarily. This is not very normally distributed. I don't like the look of this. To me, this would violate the assumption of normality. It just doesn't look very normally distributed. I got a big peak over here, and I just don't have even looking tails. But let's look at it from another way. We can also use a box plot. That shows us a distribution. And so I'm just going to drop in the name of my residuals, lm.1 resid, in the box plot. And just looking at this, to me, that median is too far to one side of the box. And this does not look normal to me from this either. So this doesn't add a lot more information, but we don't have any outliers, that's for certain, because I don't see any circles out here indicating outliers. The third plot you can check, and this one I recommend you run every single time because I think it gives the most amount of information, is something called a QQ plot, a quantile versus quantile plot. In a generic sentence, all it is showing, and let me just run it and explain what's going on here. All it's showing you is where the data should be distributed versus where the data theoretically would be if it were normally distributed. What it means is that we want our data, our residuals here, to be exactly along this line. Normally distributed data in a QQ plot is right along this straight line. And the trick with this, let me just close off this for a second. The trick with this is that you use QQ norm to bring up the QQ plot and to show you where the residuals are. But if you want the reference line where the residuals should be if they are normally distributed, you then have to add QQ line on top of it. A QQ plot is not necessarily the easiest thing to interpret on its own, but all you need to do with this is to say, hey, do my residuals follow this ideal line closely? In this case, I've got some, it looks okay. I've got some deviations here from the edges, which tends to happen. I've got a little bit of a wave in the middle here. So again, it's not, normality isn't great. It's okay. The histogram shows it a little bit too. But the QQ plot is just taking our residuals and saying, here's what quantile they actually are in. But if they were to be normally distributed, then it should be in this quantile. And that corresponds to, ideally, if they were normally distributed, landing directly on this line. So that's normality. And finally, the equal variance of errors assumption. What we do with this, we want to see how the spread of our residuals looks as we move along predicted values. So it's just a scatter plot where the x-axis is our predicted values, which is what we collected above, and our y-axis is our residuals. So let me just run this scatter plot. So remember, all this is just my predicted values, y hat along here, this axis, and their corresponding residual on this axis here. What we want to see from this is an even, random-looking distribution of points as we move from left to right. What helps us make this assessment is by using a B line and putting in a horizontal dotted line. Now I can judge, okay, do I have an equal number of points about above and below, and are they equally spaced? So starting over here, I've got some points around 10 and like -5. So not much is going on there. Once I get to y hat around 35 to 40, whoa, it really fans out. I got something probably close to 15 up here, -20 down here. That's really spread out relative to the vertical spread of these points. As I move along the y hat axis, I can see that this variance of my residuals, the variance of my errors, is actually starting to get smaller. So like at y hat equal to 50, I'm at, I've ranged from about 5 to about -5. So this is bad. This is not good error variance. We want it to be consistently distributed top to bottom as we go left to right. And we're not seeing that here. And these other plots here are the exact same thing. I'm just showing you, like I did with the histogram, that you can bring in the predicted values and you can bring in the residuals 3 different ways, depending on how you like to save your residuals and your predicted values. So everything is the same, except for the axis titles. And we can also do this with the standardized residuals. And we'll talk more about the benefit to doing standardized residuals later because it helps us look for outliers. But in any event, these distribution of residuals looks the same. It looks bad. So that's how we assess our assumptions. And you're going to do this every time I ask for it. You'll basically go through these 4 steps where you're going to do 3 sets of plots. You're going to do 1 for checking linearity. You're going to do 1 for checking normality. And you're going to do 1 set of plots for checking error variance. And then you'll just give a sentence about whether or not you think the y values are independent of one another. And that's it. And for fun, I added this on the end. I'm never going to ask you to do this, but if you want to make a scatter plot and add what a straight regression line looks like, you do the AB line command, and then you just say reg equals, that stands for regression, the name of our model. So I make a scatter plot with some nice titles. This shows the data, and I use AB line reg equal to lm.1 for the name of my model, and it pulls in the results of my model and makes a regression line. So there you go. This is our estimated regression line shown against our data. I won't ask you to do this because it gets more complicated going forward, but here it is. Thank you.